Alexa do query z Aristy, który opowie nam o 100-gigowych łączach, które są tak naprawdę kolejnym krokiem w rozwoju sieci, co wynika z coraz większych potrzeb tak naprawdę w zakresie pasma. Alexis.
Thank you. Hi everyone. Everybody at the end, some people sneaking by the door, you're welcome. I'm going to talk about something that should be quite important to you all here at the PLNOG 100 gig, the scale of networking and gaining back visibility. The first thing to discuss about is about how networking has developed differently in the last many years compared to compute CPU density, transistor density, and storage. So you might know that going from 1 gig to 10 gig, the networking industry in the past took 12 years to achieve that improvement, while in comparison, the CPU from AMD, Intel, or storage density has increased 64 times in that same period. So why that? Well, this is due to a simple aspect of networking that has been heavily based on ASICs, ASICs being the application-specific integrated circuits, meaning that the networking equipment were based on these silicons that were designed for a single use and for a specific product. The design aspect of those ASIC was actually software-based with some high-level feature requirements and then brought down, say, top-down approach where those software features were then translated into hardware. On the other around, the merchant silicon, a name for the high-density, high-performance silicon coming from the main vendors, you know, as Intel, Marvell, or Broadcom, has been designed bottom up. It means that from the beginning, the silicon was designed to achieve the highest density, the highest performance, the highest clock rate. So there's always a difference in that approach, where it achieves lower power consumption, it achieves faster, denser, and shorter time to market. While also, a side effect is, because it has got more exposure, those network silicon from merchant silicon has got more bug being discovered. Because yes, hardware has got bug, even silicon, CPUs have, network processors have, so the ASICs had. But with a better exposure, it improved the robustness. Where we are today is you've perceived in the networking equipment, mainly in the data center, a huge improvement in the densities. We went from 48 ports of 10 gig, some 40 gig uplinks, then you've seen the 40 gig coming and 100 gig started to come. So that has already been brought. And you've seen also the table sizes going from a few thousand, for example, IPv4 addresses in the table, to 4,008 and so on. So tables kept increasing. And where we are today is in this position where we've got a high density and larger table, but not yet to the highest possible. So what does that bring to us as network equipment as of 2016? Compared to 2015, just last year, you had the first, at the bottom, you can see the first 100 gig top of rack switches with a few 100 gig uplinks. Then you had 32 QSFPs per RU, or 64 in a 2 RU, and you had a density of up to 1,200 gig ports in line cards. In 2016, that density of 100 gig ports per line card is at 36. You can have 36 QSFP 100 gig per line card. In a 2 RU, you can have 48 QSFP 100 gig. QSFP 100 gig, or you might also know as QSFP 28, based on 28 gigahertz lanes. Or in a 1 RU, a high density of 1,200 gig ports with 2440 gig. Very high density, very high throughput, very compact, very dense, but also now with the ability to support full internet table on those platforms. We are talking about line cards with 36 QSFP 100 gig ports supporting full internet table at a price of roughly the same data center switch. This is commodity hardware. This is what merchant silicon brings: innovation, high density, and performance, as well as the features. I don't know if any of you have 100 gig port, but how much are you paying for your 100 gig port? The merchant silicon brings that. However, we might think, okay, all the networking vendors can do the same. You could buy a merchant silicon and build your own switch. So what's the difference between all those different networking vendors? If you're someone looking at all those platforms that maybe look alike with ports, what are the differences? The difference is in the implementation, is about the performance, the scale, the convergence time. It's about the programmability, extensibility, and the software aspect. Yes, the software is actually becoming more important than just that very latest, newest merchant silicon. As an example, how to consider that bringing merchant silicon to the one edge? Would you be ready to replace your wide area network with just merchant silicon? Have you considered that all these devices, high density coming from maybe historically data center switches, have you thought about bringing them to replace your service provider network? Are they routers? Well, the wide area network equipment has always been the highest capex in a network, and that has always been accepted as being so. The reason for those big expensive boxes for being so big and expensive is that traditionally they've been needing some very specific niche features, a lot of them, a lot of features by the hundreds, maybe the thousands, that nothing else could achieve, not even merchant silicon. And additionally, it needed very large table sizes, full internet table. Well, the fact that those are very big and expensive, that cost, is actually a very big potential for cost reduction by using that same merchant silicon that has been employed and deployed in the data center. The first thing is what you see on that graph with the yellow and red arrows are the fact that networking is becoming simpler. There is a trend in networking in simplification, in getting out of those complex design and architectures. For example, going away from MPLS RSVP to something with segment routing, label unicast, simplification, but driving the higher performance. I'm not going into the business discussion, but you know that revenue per user is not growing much, but the bandwidth is exploding. So how to get that cost down with merchant silicon? At the same time, as this curve in terms of complexity requirement is going down, the merchant silicon, because the density improves, not just in density and performance speed, also table, but also features. The pipeline is getting richer and can do more things. You can get more features in hardware. So there's a catch-up, and when those two meet up, then the merchant silicon can satisfy the requirements even as router in a service provider. The last aspect, besides these many niche features that are getting simplified, is the routing table. So today, there is no merchant silicon that can, out of the box, satisfy the table scale of a service provider or internet service provider. Nothing can satisfy the full internet table out of the box. However, Arista, with a mix of software innovation and customization, is able to fit that 1 million routes in hardware in the FIB with multiple millions of prefixes in the routes in the routing table. So that's the full internet table in hardware on the platform we mentioned earlier with a density of 3600 gig ports in a line card, or as a fixed form factor 48 per 2 RU or 12 per RU. But besides the scale, there is also the matter of convergence. Again, software improvement, software innovation, helping to beat everything that the competition has done on those routers for decades in the way a full internet table is programmed onto the hardware, because convergence matters. So where would a merchant silicon fit in a service provider environment? There is the edge aggregation, a lot of 10 gig going to 100 gig backbone, for example, or cost-effective 100 gig peering, whether it's full internet peering or some content distribution peering. Inside some of your data centers where there's a need for big data, for IP storage, cloud, NFV, network function virtualization, and also those 100 gig links, you might already have them, is how do you monitor that with your maybe 1 gig in IPS, intrusion prevention system, or 10 gig? Those very expensive systems that do need to see everything in a network. To aggregate those 100 gig links, you would also need some tap aggregation system, network packet broker, that could aggregate all those multiple 100 gig links, filter, slice, truncate, manipulate, to feed either your troubleshooting tool or your security tools. And going further into the way the service provider can benefit from merchant silicon and commoditization in the hardware is about WDM. The switch that is now becoming a router, as we've seen, can also support some LAN cards with hardware encryption. That hardware encryption, MACsec 256 bits, and WDM with up to 96 lambdas going onto a single fiber. So that use case is data center interconnect, metro area, but actually you can go up to 3,000 kilometers or up to 5,000 kilometers depending for your WDM requirements without the need for a dedicated encryption box. You can imagine how much an encryption box costs for 96 port of 100 gig for hardware encryption and WDM for the price roughly of a data center line card. Very, very cost-effective way to provide very high throughput across sites. So you can think about, in your networking journey, where is merchant silicon going to be applicable elsewhere? There are use cases. Some merchant silicon might not support the RSVP, but again, people are going for segment routing. So there are more and more use cases for merchant silicon, especially given the bandwidth, the throughput that it provides at a very cost-effective point. And why would you even bother when you have all your routers? Well, simply for the performance, for the price-performance ratio that it brings, sometimes requiring some re-engineering, some redesign, but you are probably, some of you already looking at segment routing, at label unicast, how to optimize your network, going IP, going cost-effective, very high density, very high throughput. With that bandwidth increase comes another aspect in your life that's possibly troubling, is the amount of telemetry, the amount of visibility you probably lack. So why is networking telemetry critical? Well, what you've got here are two cars. You've got a nice Mustang and the Shelly. The Shelly on your right-hand side is a racing car, an autonomous racing car, self-driving racing car that has got an enormous amount of data that it's getting from all its sensors, from the car itself, from its environment, from its conditions. And there would be no way for it to be able to race on the track and beat its human competitors without collecting all that data and processing it immediately. So telemetry is critical. But the approach of the industry to telemetry so far in networking has been the same as it has been for the last 20 years. What do you use to monitor your network? You've got SNMP using MIBs and syslog. Many don't have much more. Maybe ICMP to ping to check whether the device is alive. But what's happening is that syslog does not provide a lot of information. It's not very granular. It doesn't give a lot of details. SNMP, again, you are doing some polling every 5 minutes or every minute. It doesn't give you a lot of information, only what the MIB provides. And during those period of polling, things might happen that you would not be aware of. And your network management might have a nice graphical user interface that present the data, but it's not going to tell you more than what was already provided by the devices that don't provide the granularity, not necessarily all the information that you wish access from the device. So the Arista approach to telemetry is first on the workload visibility, the automation of the network provisioning for the virtualized workloads, such as VMware, Docker, Hadoop, and also finding those different elements in the network, whether it's physical or virtual. All the switches also have historical state database locally on the switch, so that you can retrieve the most important changes that happen. And lastly, triggered alert and state streaming. So that is important because now we are not talking about polling anymore. This is being triggered by the switch itself. This is being streamed out. Why am I talking about that polling so much? Because polling is inefficient. Whether you've got a small or large network, polling is inefficient for two reasons. First, it relies on information that's usually not very granular on the device. You know, if you've got a MIB, and that's it, how do you collect the rest of the information? There is much more on a switch. Second is, it's not very timely. So what you see here is a typical example. You are polling every minute a state in a MIB. It could be every 10 seconds, although nobody does an SNMP walk every 10 seconds. But if you were to look at something that happens often in a network, congestion, micro-congestion, that can happen within just a matter of second or microsecond. Your poll might tell at T0 that everything is all right. T0 plus 1 second, that everything is all right. Your health indicator for your network would be everything is good, which is not the case. And you would have never have any way to figure out what happened there without a trigger-based mechanism. Streaming allow network devices to send information as they occur on the switch. So there's no need to poll a device every 10 seconds or every minute. A device might not need to update something to send an update in its streaming for a month if that state does not change, for a MAC address, for example, or a routing entry, a neighbor relationship with BGP, an ECMP settings. So that allows the switch to only send information when it's required. That allows a very effective way to scale the monitoring, because now you can just send the data that you really need. So that the network may be quiet for a month and then have a lot of flaps during a few seconds. You will have all the information because every change will trigger an update in the stream. And furthermore, all that information you see in the reading glass is much more than what you would traditionally find in a MIB. That's all the states present in a switch. Some of you might know OpenConfig. That includes some limited amount of information that can be streamed as well. But these here are everything that can possibly be found on these centralized database in the switches being streamed to different elements in a network to aggregate those states. You've got some Arista Cloud Vision, for example, that can receive those streams being using some standard protocol in gRPC, different streaming protocols that are open and can be used. So the information being sent can be consumed by that Cloud Vision or by the element of your choice. That could be the ELK stack, Elasticsearch and Kibana, or going to Splunk if you have it. Log entries, Graphite, you can digest, you can receive that data the way you want. And the whole content of a switch streaming can be equivalent to roughly 100 or 200 megabytes of data, depending on the activity on the network. That's 100 megabytes of data per day that can represent a very large and very rich, it's a gold mine of information for you, for the network engineers, to either figure out what happened 1 hour ago or yesterday, a month ago, for troubleshooting, for trend analysis, for detecting some behavior anomalies. So there is performance, troubleshooting, real-time security, or something specific to the industry, whether it's service provider, enterprise, or ISP, whether it's a broadcaster, whether it's a media entertainment. You might have different ways you want to analyze that data. All the data, representing big data, that large amount of data can then be analyzed, processed the way you want, either through, again, some commercial tools or through your own tools, through your own method to digest and correlate different states. This is a graphical user interface, an example of what the portal look like, accumulating all the states from all the different devices in a network. And I'm going to show you a demo of that, what it looks like. So I'm just switching to the browser. So what you have here are different elements for a given device. I have, in this example, taken a device called Prague, and you've got a line here that shows you the evolution of the network from the different states at any moment in time. So as you scale down, as you progress in time, you see the evolution of the amount of MAC addresses you see in a table, the activity in the MAC address table, the trend is about learning and losing addresses, the amount of use VLAN that progresses across time. So you can have that whole visibility in the network, visibility of the, all these elements all at once, so that you can do some correlation at some moment in time, not just for the environment, but also for the networking aspect. Not just per device, but you can select a metric of choice. What's your favorite metric among all that? Layer 2, layer 3? Should I grab IPv4? BGP neighbor? Any choice in the audience? If I take BGP LAN path for all the devices, what you see here effectively is a list of all the prefixes that are learned by the individual devices in your network, so that you can go back on time on what it was at on Sunday night and see that you had some devices with 247 paths, 247, while another one had 1,000 and so on. And you can have that easy visibility about what your network really looks like at any point of time and how it evolves. So this is critical for the network engineers to have that visibility. So I'll finish this presentation on 100 gig, on the how the community hardware changes things for the service provider, and the importance of telemetry and how streaming can help you. Is there any question in the audience? If not, then thank you very much.